solving trig equations today, and this will be very similar to what we did when we did inverse trig functions. The difference will be today we'll have multiple possible solutions. When we did the inverse trig functions, that was a function, and so there had to be only one possibility. So we thought about sine being root 3 over 2, the y-coordinate being root 3 over 2. We knew that that was pi over 3. And for inverse sine or for inverse tangent, when we wanted a negative, we just stuck a negative on it. That was it. But now we don't just want that one particular output for this function. We want to think about all the possible angles that could have this sine value. So as we think about what theta could be, again, they'll all have to be some sort of pi over 3 angles. You know, that has to be the reference angle. But for sine to be negative, there's multiple possibilities. If we think about ASTC, we know that sine is negative in the third and the fourth quadrants. So we want the pi over 3 reference angles in the third and fourth quadrant. And again, if you know your unit circle really well, you might know what those two angles are. You can also think about kind of counting around till you get there. You can always draw it out and figure it out. You can say if I've got a pi over 3 reference angle here, well, to get this angle, I would take pi and add pi over 3. And then 3 pi over 3 plus pi over 3, that would be 4 pi over 3. Again, that would make sense if you counted around. You would have had 1 pi over 3, 2 pi over 3, 3 pi over 3 is the same thing as pi, and then 4 pi over 3 is in the third quadrant. And then we could also find our fourth quadrant angle. So we've got a pi over 3 reference angle right there. Well, that's a little bit less than a full circle. So we would take 2 pi and subtract pi over 3. And so 6 pi over 3 minus pi over 3, that would be 5 pi over 3. So those would be the two angles that we might think of first. The thing is, if we're looking for all the solutions, those aren't the only angles with that sine value. In fact, we haven't even said this negative pi over 3 yet that we used for the inverse sine, so that's another one. The issue here is that we've got coterminal angles. We've got angles that rotated in different ways but landed in the same place. And so actually, because of this, all of these equations are going to have infinite numbers of solutions. We can always add and subtract 2 pi, go in full circles, forwards or backwards, and get more angles. So I could subtract 2 pi from this one. That would be negative 2 pi over 3. Subtract 6 pi over 3, subtract 2 pi, we'll get that. You could also add 2 pi to these. If I add 6 pi over 3, then this one would be 10 pi over 3. This would be 11 pi over 3. These are all different angles that rotated different ways, but they all land in these same two exact spots with that same reference angle and have that same trig value. So there's an infinite number of solutions. So the way that we're going to represent this, you can see these notes down here. All trig equations have infinite solutions because of these coterminal angles. And the way that we get all these solutions is we keep adding 2 pi. And so we can represent all of them by looking at adding multiples of 2 pi. So I can say, the way we'll write what we'll call the general solution of all the solutions is I can say I've got 4 pi over 3 plus any multiple of 2 pi. This n has to be an integer. If n was a half, you'd only be adding half a circle. You want to be adding full circles. But it is an integer. It could also be negative, so we can either add full circles or subtract full circles. And so these are all the coterminal angles with 4 pi over 3. Then we do the same thing for 5 pi over 3. And so this represents all those infinite solutions, all those coterminal angles that have that sine value. And then this one, we're going to have a little bit of algebra to do first. We need to isolate this secant function and get it by itself. You could think about it like 3u squared minus 4 to 0, if that helps you. Again, these trig functions are kind of like one big variable, one big chunk. And so you want to solve it just the same way as you would solve this equation here. So you want to add the 4 over, and then divide by the 3. And then again, this squared is on the outside right there. That's secant of theta squared. And so we can go ahead and square root it. Square both sides. Just make sure you remember when you add square roots into the problem, you square root both sides. Got to put that plus or minus there. That's a common thing that's forgotten. That will make you lose half of your answer. So be really careful with that. When you square root both sides, put that plus or minus. We've got secant theta equals plus or minus 2 over root 3. Now, anytime you've got these reciprocal functions right here, don't replace secant with 1 over cosine. Just go right to cosine of theta equals, and just do the reciprocal on this side right here. You're more used to going the other way, where you've got cosine, and then you write down what secant is. If you've got cosine, then you know that secant is the reciprocal. But you can go both ways. If you know secant, cosine is the reciprocal. You know cosine, secant is the reciprocal. All right, well here we've got this plus or minus here, so I don't really have to think about A as TC, because if it's positive or negative, I want all 4 quadrants. All right, so I do have to think about what my reference angle is. So if I want cosine to be root 3 over 2, I want the x to be root 3 over 2 on the unit circle, and that's your pi over 6s. And again, I want all the solutions, so I need all the coterminal angles with pi over 6. So I have to put this plus 2 pi n on it. And then in the second quadrant, again, if you have to think a little bit about what the second quadrant angle with the pi over 6 reference angle would be, that's okay. But as you get to know your unit circle more, you might just start to know them. That'll be 5 pi over 6. And then I need the third and fourth quadrant angles. That'll be 7 pi over 6 and 11 pi over 6. And I add that plus 2 pi n to the end of all of those to represent all the coterminal angles, all those infinite solutions. And that's perfectly acceptable for full credit. That's a great answer right there. What actually ends up happening is that you often see it written a different way, because mathematicians are always trying to find ways to be efficient. I often say it's lazy / efficient. We're trying to be efficient. Sometimes it ends up seeming like we're being a little bit lazy. So there's a way to kind of condense these here. So what we did is we looked at pi over 6, and we just kept doing full circles from pi over 6 to get all those coterminal angles. We did the same thing for each of the angles. But if you take a look at 7 pi over 6, instead of doing pi over 6, full circle, and then separately 7 pi over 6, full circle, well, there's a more efficient way to do it. If you take a look at this, pi over 6 to 7 pi over 6. Not quite drawn to scale. This should be a little bit closer to the x-axis. That's exactly half a circle right there. They're symmetric. And so I could combine those two together. I could say pi over 6 plus pi n. If I take pi over 6 and add pi, I've got 7 pi over 6. And then add pi again, and I'm back at the next first quadrant angle right there. I can just keep adding half circles to get all those angles right there. This right here includes 7 pi over 6. Well, I can do the same thing with the other two angles. If I look at 5 pi over 6 and I look at 11 pi over 6, those are also separated by half a circle. And so I can say 5 pi over 6 plus pi n. And so these two right here are actually another way that you can write all those infinite solutions right there. Because again, this one right here would include that 11 pi over 6. Now this is totally optional. What we said up here is full credit. That's all the solutions. That's good to go. We only bring this up because you'll often see this when you're checking your answers. And so you want to just be aware of this. But the safest answer is just write all the angles and put plus 2 pi n on there. And just notice you can't always combine them together. On this last one here, They weren't quite symmetrically spaced around. The distance here is not a half circle. The distance here, the amount of rotation here versus the amount of rotation the other way around is not the same. So there was no way to combine those together. All right, so that's kind of a pain, all this plus 2 pi n stuff, all these infinite solutions. And so then what we often do is we just restrict ourselves to 0 to 2 pi. We say, all right, if we wanted all the solutions, we know we could just put plus 2 pi n on there. So let's just find those first solutions in one full circle, and that'll usually be enough for us. Okay? So if we take a look at this example here, one thing you have to be careful about that everybody right here wants to divide by sine of theta when they first see this problem. Don't do that. Don't divide by sine of theta. It's really important that you don't do that. Take a look at this note that I've got down here. So if you divide both sides by something that could equal 0, you're going to lose solutions. Take a look at a simpler problem. If we just had x squared equals x, if you divide it by x, you would only be left with x equals 1. You only have one solution. So we know x squared should have two solutions. What you really want to do, the name of the game in this that we're going to do over and over and over again is we're going to equal to 0 and factor. Make the equation equal to 0 and factor. So on this simple one here, you'd want to subtract the x and then factor it. And you see you get both 0 and 1 as solutions. If you divided by x, you would lose that x equals 0 solution. Because remember, you're not allowed to divide by 0. So if you divide by x, well, if x was 0, that wouldn't be allowed. So never divide by something that could equal 0. And of course, we know that sine of theta does equal 0 sometimes. It points on the unit circle with a y coordinate of 0. So don't divide both sides by a function. Equal to 0 in factor. Equal to 0 in the factor. That's the name of the game. All right? So to make it equal to 0, we have to subtract that sine of theta over. We'll have 2 secant theta sine theta minus sine theta equals 0. And then to factor that, we've just got a GCF theta that we can pull out. So we've got sine of theta times 2 secant theta minus 1 is 0. And then the reason why equal to 0 in factors is so powerful is because then we can use that zero product property. We've got a multiplication problem that equals 0, a product that equals 0. So zero product property says that one part has to be 0. Either sine of theta equals 0 or 2 secant theta minus 1 equals 0. And so then at this point, we just kind of got two branches of the problem to solve here. Sine of theta equals 0. This is good to go. We're going to think on the unit circle. If we want the y coordinate to equal 0, then we need to be on the x-axis. And so we've got a couple options here. Notice we had a bracket on 0 and a parenthesis on 2 pi. So we're going to call this angle right here 0, not 2 pi. And then we're going to say pi over there. All right, so that's our solutions for that branch of the equation. Then we can come back over here and finish this one up. So we'll add the 1 and divide by 2. So we'll have secant theta is a half. And again, just go right to then what cosine equals. Just find the reciprocal. Well, 1/2 the reciprocal is 2 over 1. That's just 2. So then we think about that. We want cosine of theta equal 2. We want the x-coordinate on the unit circle to be 2. Well, that's actually impossible. This branch of the equation doesn't give us any solutions. This right here is the final answer, just 0 and pi. If you're not sure why this is impossible, there's a couple ways to look at it. One way is to think about the unit circle. It was a unit circle because it had a radius of 1. The furthest out that it goes is 1. So if we tried to have an x-coordinate of 2, there's nowhere on the unit circle where the x-coordinate is 2. It's impossible. You could also think about the graph. If you look at the graph of cosine, remember I had an amplitude of 1. Started up here at 1, and then it just kind of bounced around between 1 and negative 1. So the highest the cosine graph goes is 1. It's never going to go up to 2. So there's no angles that have a cosine of anything bigger than 1. Cosine is less than or equal to 1, always. Okay. Alright, so let's look over at this next problem then. We've already got it equal to 0. Again, the most common thing is going to be equal to 0 in factor. Pretty much the only other thing we've got is just isolating. If you've only got one trig function, then you can just go ahead and isolate it, get it by itself. But if you're not isolating, then you're going to be doing equal to 0 in factor. Those are pretty much our only two trigs. So we'll factor out the cosecant squared. That's a GCF. Again, if you need to, you can think of these like with a u substitution there. You could think about that like u to the 4th minus 4u squared if you need to. And so if we factor out that cosecant squared, we'll have that. And then we can do our zero product property. So either cosecant squared is 0 or cosecant squared minus x minus 4 is 0. So then we'll solve those two different branches separately. So over here, of course, if it equals 0 when it's squared, then it has to equal 0 without the squared. You can square root both sides, plus or minus 0, the same thing as just 0. Okay, so if cosecant is 0, we're going to be looking at sine. Well, the reciprocal of 0, we'd have 1 over 0. Well, you can't equal 1 over 0. That's undefined. Well, let's try to think about when sine would be undefined. And again, that's something that's impossible. That never happens. We're not going to get any solutions from this branch of the equation. Again, you can either look at the unit circle. There's no points on a circle with an undefined y-coordinate. Every point on the circle has a y-coordinate. You can think about the graph. The graph of sine was similar to cosine. It just started at 0 and then bounced around. There were no asymptotes on the graph. There were no holes. There was nothing funny. There's no gaps in the graph. The graph was never undefined. And over here, we'll add the 4 over. And this time when we square both sides, we do have to make sure we remember that plus or minus. It's really important. So we've got cosecant x is plus or minus 2. And then just go right to what sine of x is, find that reciprocal. Again, these ones with a plus or minus, you don't have to think about the ASTC. You're just going to be looking for all 4 quadrants. So for sine to be 1/2, y-coordinate is 1/2 on the circle. That's your pi over 6. And then you just want all the pi over 6 referencing as in all 4 quadrants. You need to spend some time thinking about it, that's fine. But it'll be 5 pi over 6, 7 pi over 6, and 11 pi over 6. And again, on these problems, we've restricted ourselves to just 0 to 2 pi, so we don't have to put that plus 2 pi in for the infinite solutions. These are the only angles within that interval right there. All right, one last problem here. The issue with this one is having both the sine and that cosine right there. There's no way to isolate one of them. There's no way that we're going to be able to factor this right now with both the sine and the cosine. So the trick is to use identities. You probably remember those Pythagorean identities. We had that sine squared plus cosine squared equals 1. And so I can replace sine squared with 1 minus cosine squared. So just make sure this 2 will have to be distributed here. 1 minus cosine squared x here, 2 times all of this, 2 times sine squared, so 2 times the whole thing we're replacing sine squared with. And then now we're only going to have one type of trig function in here. Okay? And let's see, I actually meant to change this to a 1 right there. I thought I changed that already. Sorry about that. Let's go ahead and change this here. Okay, so we'll have 2 minus 2 cosine squared x is 1 plus cosine x. And then I like to keep my squared terms positive, so I'm going to put everything on the right side here. Put the 0 on the left, again, equal to 0 in factor is our name of the game. Make sure that you are making it equal to 0 when you want to factor. This is a zero product property that we have. We can't do this splitting up kind of thing, making each part equal the number unless it's zero. It's got to be zero. The key is equal to zero. In fact. Okay, so we'll have 2 cosine squared x. We'll have plus cosine x, and then 1 minus 2. Again, I did change that 2 in the problem to a 1. Sorry about that. But 1 minus 2, we'll have minus 1 here. And then you could go ahead and factor this right now if you felt like you were comfortable with that. This is a trinomial, kind of like a quadratic in disguise pattern. If you wanted to just factor with cosine and cosine instead of x and x, you could. A lot of people like to do the u substitution. So we can make u equal cosine x. And then we'll have 0 equals 2u squared plus u minus 1. And so then if we factor this, we'll have 2u and u. Again, without the substitution, you would just have 2 cosine x and cosine x. And then we'll have plus 1 here, minus 1 there. And it still equals 0. So here we'll have u equals a half and u equals negative 1. So we go back and put the cosine x in. Cosine x is a half. Cosine x is negative 1. And so here we will have to think about the ASTC. We only want cosine to be positive, and so we're only going to want the first and the fourth quadrants right there. And on the unit circle, the x-coordinate being a half, that's pi over 3. So we're looking at pi over 3, and then in the fourth quadrant, that's 5 pi over 3. And then over here, for cosine to be negative 1, we're thinking on the unit circle, we want the x-coordinate to be negative 1. That's over to the left, and that's an angle of pi. So this half gives us these 2 answers, this half gives us that 1 answer. So all together, we've got 3 different possible solutions. So just remember equal to 0 and factor. And if you want all the solutions, you stick plus 2 pi n on it. If we restrict you to 0 to 2 pi, then you don't have to worry about it.